sound good?
Yeah, it sounds good.
The music and like check.
Yep, sounds
Does
good.
that sound good?
Yep.
Gain's not too loud.
Not yet. Well, it sounds fine now.
Okay, I think it's time to get started. Welcome everyone to the Detector Virtual Workshop. It's a year-long workshop dedicated to the advancements of detectors and funded by National Science Foundation. It's a pleasure to introduce a friend and frequent visitor to RIT, Jim Beletic. I think this is his third or fourth visit here in the last 5 years or so. Dr. Beletic is Senior Director of Space and Astronomy at Teledyne Imaging Sensors, where he's been for 8 years. Before then, he was at the Keck Observatory, before then at ESO, before then at Georgia Tech, and before that, Lincoln Laboratory, before that, Harvard, and eventually going back long enough, he hails from Cleveland Heights, where he went to St. Ignatius High School, only a few miles from where I grew up. Dr. Beletic will be talking about the fantastical discoveries of astronomy made possible by detectors.
Good morning, Rochester. It's a pleasure being here. I always like coming back here. And for anyone on the internet, good morning, good afternoon, good evening, whatever's appropriate. I think this is my first internet talk live streaming. I was real proud of it, so I told my daughters, and they were not impressed at all. In fact, they looked at me and they said, "Dad, this just proves that they'll put anything on the internet." So they said they just hoped I wasn't going head-to-head with the new cat video. So my goal today is actually to beat out the latest cat video. And I think it's going to be easy to do because I got great material for you. What I'm going to try to impress on you is the importance of 2.6 materials in astronomy. In fact, one could argue that if it wasn't for the 2.6 materials, we wouldn't be able to do modern astronomy. Because 2.6 materials are used to make the most sensitive detectors in astronomy, and much of the cutting-edge research in astronomy is done with 2.6 materials. And in fact, most of the next generation telescopes on the ground and in space are based on infrared instrumentation that's based on 2.6 materials. Now, for those of you who may not be that familiar with 2.6 materials or very sensitive detectors, I'll remind you that the most sensitive detectors for visible light or infrared are based on crystal lattices. And this is a drawing here of the crystal lattice for silicon. And in these crystal lattices, they're one of the most beautiful things made in nature. It's a regular grid of atoms, kind of like the chairs in this room, but in a three-dimensional grid. And they're all connected together and held together by covalent bonds. And that means they're sharing electrons in the outer shells of the atoms. And each of these covalent bonds, there's 2 electrons shared between 2 atoms. And so if you pretend I'm an electron, can you still see me on the screen there? And I'm being shared between 2 atoms. I'm covalently bonded here. You can put some energy into the crystal lattice, either by heat or by light, and release me from the grip of the local protons that's holding me. So once I get out here, away from the grip of where I held to the crystal lattice, what do you think I see? I see completely filled covalent bonds, nothing really to grab me. I think this is kind of amazing, actually, that I'm an electron here, there's other electrons right around me, but I'm not held to the crystal lattice. If you put an electric field in the crystal lattice, so let's say this is positive and I'm an electron, I'm going to get attracted over to the positive side of the detector. Likewise, if you have an electric field this way, the hole will tend to migrate the other way, the absence of electron, because electrons will keep bouncing over to fill the hole as they try to move across this electric field. And you can collect holes at one end of the detector or electrons at the other end, and you can make detectors with either polarity. In fact, most of the 2.6 materials that are very sensitive, you actually collect holes instead of electrons. Now for silicon and the 2.6 materials, They're what you call face-centered cubic lattices. And these ones, the FCC, or face-centered cubic lattices, every atom's covalently bonded to four nearest neighbors. So you want every atom that goes into this crystal lattice to have, on average, 4 electrons in its outer shell of electron, in its outer shell. So if you're going to go look and try to make crystal lattices, you want to go to the periodic table of elements. Are there any astronomers here? I know there's at least a couple back there. If you ask an astronomer for their periodic table of elements, this is what they're going to give you. We've got hydrogen, helium, and then everything else made after the Big Bang is called metals. Well, that's not quite the same periodic table of elements we want to use to make crystal lattices. So we'll go to more conventional ones. And where you want to go in the periodic table of elements are columns 2, 3, 4, 5, and 6. And these columns here denoted by here is the amount of electrons in the outer shell of the atom. If you want to put these in a face-centered cubic lattice, you want to get an average of 4 in the outside shell. So silicon all by itself works very well. It's got 4 electrons in the outer shell, makes a very nice crystal lattice by itself. You can go to columns 3 and 5 and take half the atoms from column 5 and half the atoms from column 3 and make things like in-speed or in-gas. Those are different materials. Or you can go to columns 2 and 6 where you take half the atoms in the crystal lattice come from column 2 and half come from column 6. And so those are called the 2,6 materials, and that's what I'm going to talk about today. As Don said earlier, I worked in astronomy at different observatories, and then about 8 years ago I went to industry. And I went to a company that made 2,6 materials, and I just thought I was going to work for a company. And I didn't realize I was joining a religious cult. It's the 2,6 cult. The 2,6 is much better than 3,5, and it's the best stuff out there. At the beginning, I thought this was a little amusing, and my colleagues did not think it was that amusing, but I found it amusing. But after a while, I learned that really 2,6 materials are better than 3,5 materials. And the point of my talk here today is to try to convince you of that also. So I'm going to jump to astronomy. Oh, one of the beauties of 2,6 materials is you can change the mixture of the mercury and cadmium to change the band gap of the material. And the band gap is how well you're holding the electrons into the crystal lattice. So it's the minimum amount of energy you need to pull an electron from the valence band, where it's held to the crystal lattice, out to the conduction band. And certain materials, if you look back here, like InSB, which is one indium atom and one antimony atom, that you only can mix 50-50 and always has a set band gap. Silicon has a set band gap, but mercadtel, you can change the mixture of the mercury and cadmium to change the band gap, which changes the cutoff wavelength. So always 50% of the atoms are tellurium. If you look up here at the formula, 50% is tellurium, and the other 50% are specified by the cadmium fraction. And as you increase the cadmium fraction, that's more of the atoms are cadmium, you will increase the band gap, which reduces your cutoff wavelength. So you need stronger photons or shorter wavelength photons to release an electron from the grip of the crystal lattice. Or as you add more mercury, you make a smaller band gap and you can go for longer wavelengths. This is temperature dependent, and so you need to know what temperature you're operating when you go to make up your crystal lattice. Now, a few ways of remembering which is it more cadmium or mercury that changes its band gap for longer or shorter. One is that if you ever could play with mercury, which I don't think you're allowed to do anymore, it's liquid at room temperature and must not be holding on to its electrons that well. So as you put more mercury in the crystal lattice, you're not holding on to electrons as well, and you have a smaller band gap. Or the other way to look at it is if you go back to the periodic table of elements, you see mercury's further down the periodic table of elements, so the outer electrons are more shielded from the protons that are in the nucleus, and so it's easy to pull those electrons away from the atom. So 2 ways of remembering the polarity of how this goes. Okay, if we jump to astronomy, so I'm going to go into talk back and forth between astronomy and talking about 2,6 materials and how they're very good for astronomy. Am I in a good place?
It's good.
Too loud? Okay. So we're all lucky to live in the golden age of astronomy. It's been 400 years, a little more than 400 years since Galileo first trained his telescope on the heavens. And in the last 20 or 30 years, there's been an explosion of telescopes, of very large telescopes on the ground and in space. In space, we have the Hubble Space Telescope. It's 2.4 meters wide. The bigger a telescope you have, the further you can see in space. And we also have facilities like the Very Large Telescope facility that is run by the European Southern Observatory in Chile. And each of these telescopes here is 8.2 meters wide. This is a 2.4 meter or 2.6 meter optical survey telescope. This is a 4 meter infrared survey telescope. And these telescopes here that look small compared to these other ones are 1.8 meters, and they can be moved to these different stations so that you can actually combine the light from all of these smaller telescopes, sometimes with bigger telescopes, as an interferometer and get much better spatial resolution than you could with an individual aperture. What do we use these telescopes for? We want to measure the heavens. If you go out at night tonight, you'll see Orion in the sky. If you only looked in the visible, this is what you'd see. The reason you want to look in the infrared, you see the infrared is where the action's really going on. The brightest star in Orion on the shoulder, the red star there, is Betelgeuse. It's a red supergiant. But if you look in the infrared, that's not where the action is. It's really in these clouds here, like the Orion Nebula and the Horsehead Nebula. And in fact, in these regions here, you wouldn't even be able to tell there's anything there without looking in infrared. So you see much cooler materials and lower energy processes because it's longer wavelength. Not only can you see the clouds, you can actually see through the clouds because infrared light can propagate through the clouds. This is one of the most famous pictures taken by Hubble. It's called the Pillars of Creation. The gas cloud on the left-hand side there is about 4 light years in length, about the distance from our sun to the next nearest star. In the visible, you get beautiful images like this, but you might want to see what's going on in these clouds. So if you look at the infrared light can actually get out. Doesn't get scattered as much by the dust particles and the gas, and so you can see the star-forming regions inside. The universe is extremely huge. There's not many photons coming to us, so we would need to make telescopes as big as possible. This is one of those 8.2 meter telescopes I just showed on a previous slide. To get some sense of scale, look at the person down at the bottom of the image. This is the primary mirror that's 8.2 meters across. So the way that this works is that the light comes down, hits the primary mirror, goes up, hits the secondary mirror that's here. You can come down through a hole in the center of the primary mirror and go to this instrument here, or you can put a flat mirror here, which you see there, that will bounce the light off to this side. One instrument can go here. You can turn that mirror 180 degrees and have an instrument there. What I think is amazing with a telescope like this, it weighs about 350 tons. And you need it to move across the sky better than any Swiss watch moves as far as the movement to keep the image steady. And so there's no ball bearings in the world and no wheels in the world that are smooth enough to actually move this. And the only way you can really make it move so smoothly is float it up on a bed of oil. If you played air hockey, instead of an air hockey table, this is like an oil hockey table. You have about 100 microns thick of oil at very high pressure, but that's about the thickness of your hair, and it floats in this direction on oil, and it also points up and down in the azimuth direction on oil. This whole structure that weighs about 350 tons is all there for it to move a few ounces of material and keep it in the right position. If you look at the amount of aluminum on this mirror, that's about the amount of aluminum in an empty Coke can. There's much less aluminum on these mirrors, and then when the light actually hits an infrared detector, it's only about a 50th of an ounce, or 50 milligrams. So it's even what's that? About a 50th of an ounce, of material. So this whole structure here and all this infrastructure is just to move a few ounces of material around. Now, on the ground, you can build big telescopes, much less expensive in space, but you have a couple challenges. And one is that all the light doesn't get to the ground. If you look here, the bottom of this plot, that's the transparency of the Earth's atmosphere. You can get light down through the radio window, or you can get through the so-called optical window, which is a combination of visible and infrared. And if you look at the transmission in the infrared a little bit closer, you'll see here from the visible wavelengths that are over here, out to 1 micron, going out here to 20 microns. There's big regions where molecules like carbon dioxide, ozone, or water absorb, and you only get certain windows you can see through the atmosphere. To expand on this a little bit more, you'll see that there's windows in the visible, and then there's windows in the near infrared. We can see out to about 0.7 of a micron. And people use filters to look through these windows. They say, I'm only going to look at light coming through these windows. And they're called, given the letters J, H, K, L, and M. And what you'll see when you look at data taken from space telescopes, like Hubble Space Telescope, they'll use the same filters. Not because they've got the atmosphere in the way, because they want to cross-calibrate with images taken from the ground. There's also another real basic problem you have when you want to look through the atmosphere, and that's atmospheric distortion. You see it every day, and you look at shimmering across a hot parking lot. And the resolution you should get on a telescope is given by the wavelength divided by the diameter, and you should be able to see to a resolution of one of these small features here that's called the speckle, but the atmosphere is blurring that out to be much bigger, and over a longer exposure, you only can see very gross features. Unfortunately, this animation doesn't play on this computer, but this shows you that the distortions are correlated over small angles in the atmosphere, and so you should be able to set up some kind of optics to correct this distortion, and that's called adaptive optics, and I'll come back to that later on in the talk. So if you had all the money in the world, why don't you put a telescope in space? And that's what the Hubble Space Telescope is. 2.4 meters wide, and in May 2009, the last servicing mission, they upgraded to a new instrument called the Wide Field Camera 3, and in there is a 1 megapixel sensor made out of 2.6 materials. Now, I said you could tune the band gap of these materials, and this one was tuned to have a band gap, so the longest wavelength you can see is 1.7 microns. And that is because as you make the band gap longer, it's easier to shake electrons out of the crystal lattice, and any thermal energy will actually shake electrons out of crystal lattice, and that's called dark current. And they didn't want to put a closed cycle cooler like you have in your laboratory with the whole compressor and all that. Of course, they can make them much smaller. But they didn't want to have that because that could break in space. So behind the detector here, that's just 1 megapixel, much less than you have in your cell phone camera. Behind here is a 6-stage thermoelectric cooler. So solid state cooler, you put in current and you get the detector to cool down. And they said, what's the coldest we could get that? Well, that's about 145 degrees Kelvin. So at what point does dark current start to eat us? And you do the trade-off, and they wanted a 1.7 micron cutoff detector. And that was one of the good properties of the 2.6 materials. If you look here, it gets fairly high readout, a fairly high quantum efficiency, nearly 90%. It has low dark current, that on average per pixel, only 1 electron's popping out every minute or every 50 seconds. It gets okay readout noise, but take a note of this number here, 25 electrons, because we'll look at more modern detectors to get lower noise. And since May 2009, this instrument's been operating flawlessly, taking images like this. I think this is one of the most beautiful images they took. It looks like artwork, right? It's one of your design students put together. This is not a collage of images. This is what one portion of the sky looks like. It's 1/7 the diameter of the moon. But you need a 2.4 meter telescope and a 23-hour exposure to take this image. This is a collection of 5 galaxies, anywhere from 40 million to 280 million light years from the Earth. And this is showing colors both infrared and visible in this image. Now, as beautiful as this image is, and as much science done with this image, a more important image scientifically is this one. And this is only displaying colors taken in the infrared. Remember I showed you those filters, the J filter and the H filter? This has light from the Y, J, and H filters taken with the infrared camera. And this was purposely pointed at a very dark part of the sky, where pointed away from the plane of the Milky Way galaxy, where there's only a few stars in this image. This is a star, I think this is a star, and I'm not sure if there's another star in here. Everything else here is a galaxy outside of our own, and these are all shown in infrared light. Now, the most important part of this image is right down in here, and you really can't see it, so let's blow it up a little. And you see right in here, there's a galaxy that you can only see in the reddest filter. That must mean it's very far away, because the expansion of the universe since the Big Bang has redshifted the light, so even ultraviolet and visible light The wavelengths have gotten stretched out as the universe has expanded, and you're only seeing it in the longest wavelength filter. To my knowledge, this is still the furthest object yet found in the universe. This light was generated about 480 million years after the Big Bang. That's about 3.5% of the age of the universe. It's a very small galaxy, so only about 1/100th the size of our Milky Way. But it's given astronomers the sense of how galaxies started to form very early in the universe. But the Hubble Space Telescope has one very basic problem, and that's thermal radiation. Thermal radiation is anything, you people sitting right now, your atoms and molecules are shaking, you have electrons attached to your atoms, those are just like little antennae giving out radiation, and you'll give out radiation of all different wavelengths. For humans, we'll give out radiation that's peaked at about 10 microns in the infrared. You need an infrared camera really to see us. As you get to warmer objects, you give off radiation. This is wavelength here on a logarithmic scale and intensity on this scale. As you get to warmer objects, you get more radiation at all wavelengths. The peak of radiation keeps moving towards shorter wavelengths. So something like Betelgeuse that we looked at, a red supergiant, it's actually giving off most of its radiation in the infrared, but it looks reddish to us. Our star looks yellow to us because that's our eyes adapted to be peak at these wavelengths since we evolved around the sun. But then the bright blue stars that are much hotter, they have the peak radiation in the ultraviolet, but they look bluish to us. So does this make sense? Blue stars are hotter, red stars are cooler? Okay, now go to the bathroom and you want to turn on the hot water, you probably want to turn on the blue faucet, right? Or if you're in your car and you want to turn on the heat, you go to the blue on the temperature dial. Oh, wait a second, I got it backwards. Screws me up all the time. Every time I go to the bathroom, every time I go to the car, I look and I say, I want to get hotter, I'm going to turn it to blue, and then I have to rethink and say, oh yeah, I got the color code wrong. So the whole purpose of this talk is not to really show you anything, teach you anything. I'm just trying to screw up more people in the world so that when they look at those faucets, they get messed up. So the Hubble has the same problem. It was ground on the Earth in room temperature. The mirror was figured to be very precise. And when it was put to space, it was not made to get cold, so there's heaters on the back of it. It's kept at room temperature. Normally it get much colder in space. So it's kept at 70 degrees Fahrenheit. It has heaters on the back, and it's giving off radiation here, starting at about 1 micron, increasing. So it's really not that good for infrared. You want to have a cold telescope that's not emitting infrared light if you work in the infrared. Oh, for those of you who are students, this is a picture of your future work environment. There's one person working here, there's quality assurance, watching that person working, and there's 4 managers talking about it. So if you want a cold telescope, in space, you do something like WISE. WISE was an all-sky infrared survey intended to give the deepest map of the infrared sky to find what objects are out there so future telescopes could go study them more. This is the WISE spacecraft on the right. Inside of here is a relatively small telescope, 40 centimeters in diameter, but it's kept very cold. It was kept about 20 degrees Kelvin, just above absolute zero. To get a sense of the size of the spacecraft, it's about the size of a large polar bear, about a little over 9 feet tall, weighs about 1,400 pounds, and it had 4 imaging sensors, 2 of which are made out of 2,6 materials, that's why I'm showing them here, that have cutoff wavelengths of a little over 4 microns, a little over 5 microns, used to sense the 3.4 and 4.6 micron bands. And it also had 2 1 megapixel sensors that were made by DRS that were made out of arsenic doped silicon that looked at the longer wavelengths. Over a period of 8 months in 2010, I think it was 2010, it did its all-sky survey. It took images of the entire sky. If you want to see beautiful images, go to the WISE website. It took pictures like this. If you looked at this in the visible, all you'd see is a few stars. You wouldn't see these gas clouds. The star in the middle is a star about 24 times the mass of the sun. Or about 20 times the mass of the sun. It's flying at 24 kilometers per second. It has a solar wind that's blowing off gas. That gas is interacting with the gas of the interstellar medium and making this bow shock like you see here. To keep everything very cold, it had a solid cryogen, solid hydrogen, and that ran out after 8 months. But these shorter wavelength detectors that sense the 3.4 and 4.6 microns kept on working at that time. So they did a survey of the asteroids near the Earth and actually wanted to demonstrate something relatively basic. And that is that you can see asteroids much better in the infrared than in the visible, and especially tell their size. In astronomy and planetary physics, reflectivity is called albedo. And high albedo objects that are small, like this one up here, will give you the same brightness in the visible, reflecting sunlight, as a large low reflectivity or low albedo object, or albedo. Where in infrared light, you're mainly looking at emitted light that depends on temperature. So a bigger object, these are all about the same temperature, is going to give you a brighter signal than a smaller object. And you want to find asteroids that are bigger than about 100 meters. That's where they get dangerous. That's where if they hit a big city, it'd make a lot of problems. But actually an even bigger issue than hitting a city is if it lands in the ocean, it'd make a big tsunami, and that could wipe out a lot of cities. So they did a survey over a period of 4 months, and they found that on average there was less asteroids than we thought they were out there, but of course they didn't get a chance to see all of them. And there will be an asteroid survey sometime within the next 10 years, and I hope myself and some people in this room are working on that. We're actually collaborating with the University of Rochester and some work related to that. But that was, you had Hubble, which was a relatively big telescope, 2.4 meters per warm. WISE, a small 40 centimeter or 16-inch wide telescope. Cold, what you really want if you want to do astronomy, is a big cold telescope in space, and that's the James Webb Space Telescope. This will be about 6.5 meter diameter mirror. It's so big it won't fit, and there's no spacecraft that you can fit this in. So it's got to be folded up. It's a segmented mirror. And now you want to keep this very cold to about 50 degrees Kelvin. You don't want that mirror to see the sun ever. You don't want it even to see the Earth. The thermal radiation from the Earth would heat it up. So you have this tennis court sized sun shield that will reflect away the thermal radiation from the Earth and the sun. And you need to put it away from the Earth to do this. So there's a lot of space missions now going to something called Lagrange point 2. As you probably know, all the planets, as they get further away from the sun, they take longer to go around the sun. Just a general rule of gravity. So if you put an object out away from the Earth, further away from the sun, it should take longer than 1 year to go around the sun, unless you go to this point called Lagrange point 2. And at this point, a satellite's being pulled not only by the gravity of the sun, but by the gravity of the Earth. So it'll orbit the sun once per year and stay in lock sync with the Earth so you can communicate with it. So Lagrange point 2 is a popular place to put telescopes. Another place that's actually very good is Lagrange point 1, which also a satellite put there orbits once per year, because it's being pulled in both directions by the Earth and the sun's gravity. And this is where observatories that just want to look at the sun, with those are put, like the Solar Dynamics Observatory. So if you look, Lagrange point 2 is about 1 million miles, 950,000 miles away from the Earth. So about 4 times the distance from the Earth to the Moon. And if you look here on the right-hand side, you'll see you have the telescope kept cold, the sun shield. These are solar rays to get some energy. And then here's the Earth and the Moon, and then you have the sun over here, 93, or in this case, 94 million miles away. So if you thought those pictures from Hubble were great, wait till you get the James Webb Space Telescope. And for Hubble, it's a relatively small mirror, a little bit bigger than a person in diameter. It's a warm mirror. It only has a 1 megapixel infrared sensor. James Webb Space Telescope's going to have a 50 degree Kelvin mirror, very cold mirror, with 63 million pixels that are sensing the shorter wavelength infrared. There's also 3 million pixels of longer wavelength infrared, but since it's not 2.6 materials, I'm not showing it here. That's arsenic dope silicon. There is a 4th instrument. These instruments, this one here has 5 micron cutoff detectors. This is a spectrograph. This one's actually guiding the telescope. It's called the fine guidance sensors, and will do science. These are also 5 micron cutoff detectors. And then there's a camera that has 2 5 micron cutoff sensors and 8 2.5 micron cutoff sensors. Now before on Hubble, remember the readout noise was 24 electrons. Here the readout noise, the total noise, after a 1,000 second exposure is supposed to be less than 6 electrons. and some of the detectors are making that. And that's a combination of dark current electrons being shaken off the crystal lattice just for me, and it's also a combination of the readout noise. So the detectors are much better these days. And one reason is if you get 2,6 materials very cold, the dark current's extremely low. This is temperature on the horizontal scale and the linear scale, and this is dark current logarithmic of the number of electrons per pixel per second. And the James Webb Space Telescope is going to operate at 37 degrees Kelvin. And so that's right about here. And you can see here for 2.5 and 5 micron cutoff detectors, you only get a few electrons per pixel per 1,000 seconds. This is 10 to the minus 3 here. So dark current is really not an issue, it's just readout noise. And so you basically don't have to worry that much about dark current if you can get things cold enough. So we're going to go to the demonstration. Does everybody have an Easter egg that came in? And I'm sorry for the people on the internet. But in these Easter eggs, we're going to try to demonstrate how very sensitive these detectors are. So the James Webb Space Telescope, the nominal light operating time is 5 years. Of course, we all hope it goes about 10 years or longer. And during that time, the imaging cameras and the spectrographs are going to operate continuously. They're just going to keep taking pictures. There's never a daytime, nighttime. It's always in the dark. And over that time, they'll take about 1 million images on these 2K by 2K sensors, these 63 million pixels. And if you add up all the energy of all those photons that are each about 1/2 an electron volt, which is hard to get a sense of an electron volt, right? Pick up an electron that's really small, drop it through a voltage potential of 1/2 volt. I can't get any sense of it. But you can add up all the energy of all those photons, and it's the same as picking up a peanut M&M. I'll get one that's a little bigger here. Picking up a peanut M&M and dropping it 6 inches. So you can convert gravitational energy to electrical energy or photon energy. And that's the total amount of energy over 5 years by all those instruments detecting photons. Isn't that amazing? I just think it's incredible. It tells you 3 things. It tells you, one, how very weak infrared photons are, because that's a lot of images. Second thing it tells you is how sensitive all these detectors are, that they can detect that small amount of light. And the third thing it tells you is how very much science you can do with such little energy. It's really amazing. So if you look at it, it's the same amount of energy as just the gravitational energy of dropping the peanut M&M. So, okay, you can go ahead and eat all these now. So how do we make these sensitive detectors? You need really 2 basic things. You need a material that can very efficiently converts photon energy to free electrical charge. You collect that charge in pixels, then you need very sensitive amplifiers that can sense a few electrons worth of charge. So this material we grow 1 atomic layer at a time. And to make a crystal lattice, you have to start with a crystal lattice. So we start with a crystal lattice called Cad-Zinc-Tel. Here's one of the wafers here. And you start with wafers, these square wafers, this here, 5 by 5, 6 by 6, or 7 by 7 centimeters. You grow the material on there 1 atomic layer at a time. It takes about 1 second for every atomic layer. It takes about 4 to 6 hours to grow 1 detector layer, as we call it. Then you need the pattern net to collect the charge. You put little indium bumps on every pixel because you want to connect electrically to your amplifiers that you make out of a CMOS readout circuit. So this is your CMOS readout circuit that gets made in one of the big CMOS foundries. They come in these 8-inch wafers. This one has 12 of those H2RG to 2K sensors. And when you've completed a sensor and put it together, it looks something like this. You bring the wires out. And it takes 3 technologies. One, making a very sensitive readout circuit. The other, growing very high quality material and processing. And the third thing, being able to put these things together. Each pixel is only about 18 microns across. So that's 1/5 the diameter of your hair, and you got to line that up just right, those bumps. Push it down hard. I'm not allowed to tell you exactly how hard you push it down, but it's about 4 of us standing on it at one time. That's about how much pressure you have to put on, and you can't let it slip while you're doing it. So hybridization is part of the trick. Now when you grow the detector layer, you only grow for the wavelengths that I just showed you there, about 5 to 7 to 10 microns thick of material. But the crystal lattice you start with, this Cad-Zinc-Tel wafer here, is about 500 to 700 microns. So you grow the crystal lattice here, you pattern in, you put indium bumps, you flip it over, you put it down on your readout circuit, and now the light has to come through the CAD-Zinc-Tel substrate to get to where you actually want it to get. So you've got 500, 700 microns of CAD-Zinc-Tel and just a little thin layer of mercantile. That CAD-Zinc-Tel is the last thing you want there after you make the detector. Because CAD-Zinc-Tel is used for sensing cosmic rays and X-rays. They get absorbed in the CAD-Zinc-Tel, they fluoresce, they give off light, they get sensed in a detector. So here's showing you a detector under radiation, right here and here, of different cutoffs that you're seeing the radiation detected in the substrate. You remove that substrate by polishing it, if you've ever polished a mirror, and in a select polishing or actually milling it, like with a milling machine, a very special milling machine. And then at the end you do a selective chemical etch to remove the CAD-Zinc-Tel, and then you process the backside. And when you have substrate removed material, now you don't have a cosmic ray detector sitting right in front of your infrared detector. There's another benefit for doing this, and that is that the CAD-Zinc-Tel absorbs visible light. So if you look over here, visible light's 400, 700 nanometers, and CAD-Zinc-Tel absorbs shortward of 800 nanometers. And this has the substrate on, where the quantum efficiency here, the amount of light you're detecting, as a function of wavelength. You can bring the quantum efficiency up to 80 to 90%. You can put on a better anti-reflection coating. You can remove defects at the surface. And you can actually sense from the ultraviolet all the way out to whatever your cutoff wavelength is in the infrared. So there's more and more instruments now that will use a single detector for combined visible to the infrared. You may have heard of the Moon Mineralogy Mapper. That detected water on the moon, and that was a spectrograph that sensed from 380 nanometers in the ultraviolet out through 3 microns in the infrared with one very small detector in a so-called hyperspectral imager that I think some of the people work on here at Rochester Institute of Technology. Okay, stepping back to astronomy, I think we're all very fortunate. The speed of light is not infinite. If you don't like Twitter, if it's just too much information coming all the time, maybe a lot of people here actually do like Twitter. If light traveled infinitely fast, it'd be like Twitter on steroids. You would constantly get all the information of the universe and they'd get it about you. So it's actually kind of a blessing that light doesn't travel infinitely fast. It also allows you to look backwards in time. Because if you look at light that has come from a distance, it's light that was generated a while ago. For instance, if you look at light from the sun, it's light that left the sun 8 minutes ago. If you look at light from Pluto, which is still a planet to me, that left about 4 hours ago. If you look at the closest star, that's light that's traveled with us for 4 years to get to us. One of the galaxies in our local group called the Andromeda Galaxy, that's 2.9 million light years away. So if you hear of a supernova went off in the Andromeda Galaxy and astronomers are studying it, well actually, and they say it happened last night, well actually it happened last night plus 2.9 million years ago. What's the farthest we can see in the universe? Is it how big the universe is? No, no way. It's limited by how far back you can look in time. Right? So you're limited by the fact that the Big Bang happened 13.7 billion years ago. And a great question to ask astronomers, if you ever want to quiz them on things, is ask them how big the universe is. And you get a whole bunch of answers. You get very practical people like the universe is really big and you can't see beyond 13.7 billion years of light travel time. So why don't you just study that? But then if you talk to more theorists, they'll say that the size of the actual universe compared to the observable universe, what we can see is about relative to the size of the observable universe to the size of Greater Rochester, which is really amazing if you think if you put all the galaxies within Greater Rochester. But it depends who you talk to. Not only is the universe big and you can use it to look back in time, it's expanding, and this was all discovered by Hubble. It must have been amazing being around when Hubble. You know, in the early 1920s, everybody thought the Milky Way was the entire universe. And then he discovered these nebulae are actually galaxies beyond our own. And then he looked at the speed of those galaxies relative to ours, and he saw the further he looked, the faster they're flying away from us. So if you run this whole thing backwards, if everything's flying away from everything else, you run it backwards in time, there must have been a time it was all together in a very small place and had this big bang and blew up. Now if you look at his original data here, that was published in 1929, the slope of this graph's off by a factor of 7. You actually had it expanding much faster than you thought it would. And if you look at more recent data, you'll see that the Hubble constant, the speed of galaxies going away from us, is on the order of 68, 70 kilometers per second per megaparsec, and a parsec's 3.3 light years. So a megaparsec is about 3.3 million light years. At first, Einstein thought this was nuts, the Big Bang, and he said he thought there was some special force pulling up the universe against gravity. And he went to his grave thinking that that was one of his big mistakes. He might have actually been onto it. Maybe he was thinking there was some special force called dark energy. Now, how do we quantify how fast things are flying away from us? It's by the redshift. That's what wavelength of light do you see that's emitted by a star, and you subtract that from what you actually see. Well, you take what you see minus what it would be when it got emitted there, and then you divide by the emitted wavelength. So a redshift of 1, where z equals 1, means the wavelength's twice as long. If you look at a galaxy about 1 billion light years from us, the redshift has moved these absorption lines somewhat in the spectrum. But a very good tracer for looking out further distance is the Lyman alpha line. This is where the excited state of hydrogen collapses down to its ground state and emits light in the vacuum ultraviolet. The 1216 angstroms are 121.6 nanometers. Now you can see 400 nanometers, about the shortest you can see. So there's about 1/3 the shortest wavelength you can see in the blue. But as the universe expands, if you get a redshift of 2.8, it means you've stretched out that light by a factor of 3.8, and the light actually looks in the blue to you. As you get objects further in the universe, redshift of 4.4, you're now in the red part of our spectrum. And then when you get to redshift of 6.3, you've actually shifted that ultraviolet light all the way through the visible out into the infrared. And the galaxy I showed you from Hubble, that was a redshift of about 10. So you're only seeing it out at 1.65 micron wavelength. So you're seeing the Lyman alpha emission way out here. So if you want to look very far away in the universe, because of the expansion of the universe, all that light's been redshifted into the infrared, and you really have to use infrared detectors. And most of the astronomy missions are planning on using 2.6 materials to look deep in the universe. So if you want to look at the big picture of the universe, what's happening if you look close by, this on the horizontal scales, time, and the vertical scale, size of the universe, is kind of artistic drawing to tell you what people are thinking now. If you look at the closest galaxy, it's a linear plot. The further away they are, the universe is expanding linearly as a function of time. Now what you'd like to know is what's going to happen in the future. If there's no gravity, it just keeps going on forever. If there's so much gravity that you get a big bang and you come back to a big crunch, or is it just the right amount of gravity? And I think this was very popular in the early 1990s, was there's just the right amount of gravity. It's not going to be so much that you're going to pull it to a big crunch. It's not going to keep expanding forever. How do you actually figure out what's going to go on in the future? Well, we can't see the future, but we can look in the past and try to see which of these curves you're on. So you want to look at very bright objects and try to figure out how much the universe has expanded. And people have used something called type 1 supernova. Stars that blow up that are almost all the same brightness. You measure how bright they are, you know how long ago they blew up, because light just expands into a sphere. You measure the redshift and you see how much the universe expanded since while that light has traveled to you. So they looked at these type 1A supernova, published their results in 1998, and they found they weren't on any of these curves. Actually, you're somewhere off over here. And the present theory now is that we had the Big Bang, gravity started to slow down the expansion, and started to pull the universe, slow down the expansion. But now there's some mysterious force called dark energy pushing us apart, and we're going to actually just keep on expanding and accelerating our expansion as a function of time. This is called dark energy, and if you look at what the universe is made out of, that whole periodic table of elements is about 4% of the mass energy in the universe. There's about 6 times that much, about 24% of the universe is dark matter. And the regular matter and the dark matter affect the gravitational field. And so around galaxies, you have gravity pulling towards these galaxies, pulling matter towards it. But then overriding all of this is dark energy, that as you create more space, there's more and more dark energy. Dark energy is one of the primary mysteries now in astronomy that people want to solve. And every 10 years, astronomy puts together a review of what should be studied in the next 10 years. The last study came out in August 2010 and said dark energy should be the primary thing to study. Last October 4th was a kind of special day. The Nobel Prize in Physics was awarded to the people who led those groups in dark energy. Later on the same day, the Europeans announced that they're going to fund a dark energy mission to look further back in time to try to measure those supernova and a number of other things to try to see which of those curves we're on. They're planning to use 16 of the type of sensors that are in James Webb Space Telescope. These will go out to 2.4 microns. At some point when the James Webb Space Telescope goes up and there's money to actually do a U.S. mission, there's going to be a U.S. mission called the Wide Field Infrared Survey Telescope, and it's going to use similar type 2.6 detector materials. How are we doing time-wise? 5 minutes, okay. We won't get to the rest of the time. Okay, I'm going to just give you a sense of on the ground. On the ground, you can't afford all space telescopes. So on the ground, there's places like I showed you in Chile, and there's also telescopes like this in Mauna Kea. You do have a problem with atmospheric distortions. So there's this technology called adaptive optics to overcome the distortions. And what you do is you bounce the light off a deformable mirror to correct the distortions on the Earth's atmosphere, and you measure the residual distortions with something called a wavefront sensor, so that your science camera gets much better images. I think this is the best animation I've ever seen made for adaptive optics. This is a Gemini 8-meter telescope that's on Mauna Kea in Hawaii. And to try to eliminate distortions, they open it up to let the air come in and get everything at the same air temperature, because it's differences in air temperature that cause those distortions. The light from a star hits the entire Earth, but if you look at the part that's collected by the telescope, it'll hit the primary mirror, in this case about 8 meters wide, hit the secondary mirror. And for this telescope, the instruments are placed behind the primary mirror. One of them is an adaptive optics instrument that works schematically like this. Normally the light would come to focus, but what you do is you collimate the light and make a beam out of it. And if you took an image of the distorted light for a star, you'd see something like this, those speckles I showed you before. And that's actual data from the telescope. Those speckles are caused by distorted wavefronts. If you can measure those distorted wavefronts by something called a wavefront sensor, there's different ways of doing that. You can bend this mirror so that when the distorted wavefronts hit it, they come off more like a plane wavefront. Turn on your adaptive optics, you see something like this. Most every major telescope has this now. And to give you a sense that it actually works, this is a star with adaptive optics off, and then you turn it on, and you can see a much better image. Why would you want to use this? Well, one thing you might want to do is look in the center of our galaxy to try to see the black hole there. And the way you see the black hole, well, you can't actually see it, but you can see its gravity effect on the stars in the region of the black hole. So as you turn your adaptive optics on, you can see stars in the center of our galaxy. If you plot those stars over about a period of 10 years, you can see that they're orbiting a very massive object which you actually can't see. So I point out you should look at SO2 and SO16. You can see them just ricochet around a very massive object. If you do your basic gravitational calculations, you can figure out that there's a mass of about 4 million suns packed into a very small place there. So we have a black hole at the center of our galaxy, just like most galaxies. There's two leading groups that do this out of UCLA and also out of Germany. And these people someday may get a Nobel Prize for this. They keep winning awards for their work. It's good they're competing with each other. We're also in a golden age of astronomy on the ground. In the last 20 years, there's been first light on 17 telescopes with apertures bigger than 6.5 meters. They're put in Hawaii, they're put in Chile, are very good spots. Texas being Texas, anybody on the line from Texas has to have their own telescope, so they've got a big one out there. Arizona's a good place for telescopes, and also South Africa and in the Canary Islands. So this is just in the last 20 years, these telescopes have come online. If you plot the size of those telescopes, the amount of glass, and add that all up, it's about 1,000 square meters. That's nothing compared to what's coming. We're coming on a generation of the extreme large telescopes that are going to be 24, 30, and 39 meters in diameter. The whole point of these telescopes are to look in the very distant universe, collect a lot of light. The expansion of the universe has made it that light shifted in the infrared. 70 to 80% of the instruments here will be in the infrared using 2.6 materials. So I'll finish with two slides here. One is to talk about the state of the art. You can now get 2K sensors. We're now developing a 4K sensors, made the first ones. The leaders in doing this is our company, Teledyne, and also Raytheon. You get high quantum efficiency. You can get very low noise where dark current's not an issue. But there are some challenges. There are things like persistence, where you get an after image from a bright image from charge caught in traps. Not every pixel works, either because it didn't even bump, didn't touch, or because there's some defect in the crystal lattice. And these detectors, too, cost a lot more than CCDs. So we're working on bringing down the cost. So if you think the last few years have been great, wait for the next 10 to 15 years. We'll figure out how the universe has expanded as a function of time from the dark energies, how the galaxies and the stars turned on at the end of the dark ages with James Webb Space Telescope. There also will be studies of looking at planets around other stars. Right now we're just finding a lot of planets. It's time to start studying them. A lot of people think you should do spectroscopy and infrared to not only figure out the temperature of the planet, but to figure out to see methane and water, the signatures of those. And then of course we want to find a killer asteroid before it hits the Earth. So probably within the next 10 years, there'll be an asteroid mission to do a survey of all the potential near asteroids. So thank you very much for your attention. And while I'm taking questions, I'm going to put up a slide of a detector workshop that's going to be held in October 2013 in Florence. Ask your funding agencies and your professors to pay for you to go over. It should be a good workshop. Thank you very much. Questions?
Okay, we have we can take questions here. We also have a question from online asking about what's the comparison between INSBE and other 3.5s versus WorkCAD for say detectors with cutoffs less than 5 microns.
Can they hear the question?
Yes, yeah, so they can hear that question.
I don't need to repeat the question.
No, you don't have to repeat.
Okay, so INSBE is a 3.5 material where you take half of indium, half of antimonide. You put that together and you get a cutoff wavelength of 5.5 microns. You can't adjust that. So you get stuck with that cutoff wavelength. If you only want to work with shorter ones, you can't tune the material. Also, INSBE, there was a plot in there that I won't go back to. Dark current has much higher dark current than high quality WorkCAD tel. So even for 5.5 micron cutoff, you get several orders of magnitude lower dark current than WorkCAD tel. INSBE is less expensive to produce, and so that's one of the challenges in WorkCAD is bringing down the production. In gas, if you do lattice match in gas, it has a cutoff wavelength of about 1.7 microns. As you cool it, the cutoff wavelength gets shorter. You can do lattice mismatch INSBE to extend the wavelength cutoff, but then you usually get higher dark current. So if you're going for beyond 1.5 microns, you could, and you want the very highest quality, you need to go to something like WorkCAD tel. Night vision devices, 3.5s are much less expensive to produce, so things like night vision goggles and so on often are based on EDS.
Okay, we can take any questions here. Zoran?
If I had enough money to come to you, are there any technical limitations to building a, say, equivalent to a visible detector at 10K by 10K or larger? Or
So
is it just yield and enough money to do all that?
So this is a question from Zoran Nimkov that said, what are the physical limits to building very large infrared, monolithic big infrared detectors? Let's say money wasn't any object, so my kind of guy. There's some basic limits. We grow on a crystal lattice, and there's limits of how big we can get that crystal lattice. And right now it's 7 by 7 centimeters. people are growing on alternative substrates. Well, first of all, you can try to make those substrates of CAD-Zintel bigger, and maybe there's some developments that way. Or you could grow on alternative substrates like silicon, which is very inexpensive. To get a big wafer that's very smooth. But the lattice spacing of silicon versus Mercatel is 18% difference. It's like putting eggs in an egg carton. If you have the wrong size egg carton and you try to put the eggs in, they don't line up right and they get jumbled up. And then there are some other materials, alternative substrates. So we're pursuing that, other companies are doing that, where you can make them bigger and less expensive so you don't have that expensive substrate. But that's just one part of growing the material. Then you've got to process it, put in implants that collect the charge. Then you have to hybridize it. You need a bigger hybridization machine that can line up and press down. Our company right now is limited to about 6 by 6 centimeters. You can buy bigger machines that can hybridize the bigger, to 8 by 8 centimeters and larger. Some other companies do have those bigger machines, and one of these days we'll get one of those bigger machines. You also have to think, even if you could physically make a bigger detector, can you yield it economically? And whether it's CCDs or Mercatel or anything, there's usually a dip in the cost per pixel as a function of size. That it's not worth it. It's better to just mosaic mini detectors as opposed to trying to make one big one. But right now our limit's of 4K, 15 microns.
I think we had another question here.
Are you looking into any kind of epitaxial lift-off technology to be able to reduce your substrates like you do in solar cell computing?
So the question was, are we looking at epitaxial lift-off to try to remove the substrate?
Yeah, so instead of polishing and then etching your substrates off, just putting a release layer that you can chemically etch and heal your CCD or your detector.
So the idea is grow on a release layer and then pop that off. You'd have to have the right crystal lattice spacing and be a good crystal lattice. The short answer is no. I'll have to ask our material scientists.
They're doing that with the highest efficiency world record solar cells. They're all very, very thin. They're less than microns thick, and they're grown on substrates that then peel off. You can reuse the substrates again and again.
Yeah, I can't fully answer that question. I don't know enough about the technology of the drawbacks.
Jim, you hit it right on the lattice. You're not going to be able to match a lift off. I don't think that's going to work.
Yeah. There's
Was there another question? No. Okay, I had one last question, and that is, do you have any sense of what could be the big 1 or 2 developments in the next 10 years for detectors that serve these kinds of applications?
So they heard your question?
Yes.
Okay. So the big developments, I think, are things like avalanche photodiodes, and I didn't get a chance to talk here. Mercatel is a very manageable material. It's a direct bandgap semiconductor, where silicon's an indirect bandgap semiconductor. And one way of thinking of that means it's extremely efficient at converting photon energy or electron energy to free charge. And so if you get light in, you only need a couple microns thick of the Mercatel to absorb all the light. You don't need it 7 to 10 microns. We do that because we're putting electric field across it. We have buffer layers, all kinds of things. You only need a few microns thick, and then basically all the light that gets into the material is absorbed, converted to charge. Likewise, when you get an electrical charge, if you accelerate that charge through the field and it picks up enough energy, it'll pull more electrons off the crystal lattice. And as opposed to things like photomultiplying tubes and silicon avalanche photodiodes, you get a very well-characterized amplification with not much what's called excess noise or a very tight pulse height distribution. And so Mercatel APDs, electron avalanche APDs, is I think something that's going to be a new wave. But to do this, you have to actually collect electrons. All of our technologies, we collect holes. So if you're not collecting electrons, you can't be accelerating them. So there are several companies in the world that are pushing electron avalanche APDs. The drawback of those right now is they have relatively high dark current, and maybe it has to do with its harder to passivate a surface where you collect electrons in material. I'm not sure. So I'd say electron avalanche APDs. I'd say just improving the quality of long wave detectors. In general, it's harder to make high quality long wave detectors. So getting those so they have lower dark current and higher operability is something you'll see, as well as trying to bring down the cost of these detectors so you can make big mosaics. You know, if you look at something like Hubble, I think this is amazing. And you bring the light to focus, it has a image plane about this big. I think physically it's about this big, right? Anybody here to work with Hubble? You know how much of that they use? Like this much and this much. That goes into one camera, goes into another camera. Same with those big telescopes. The light will come hit the primary mirror, hit the secondary, comes to focus, and the image plane's about this big. And one instrument looks at these 4 galaxies here and pulls off the light. It's really kind of crazy. So if I can tell you a story. Pretend you're a photon. You've traveled for billions of years. And you're going along, and then suddenly you realize you're going to hit the Earth. And you're like, oh, it's over. So you're with all your photon friends here, and you're like, okay, one last drink. We're going to get smashed. And then you say, wow, wait a second. We're going to hit a telescope. We're going to get in a picture book. We're going to be part of a picture. You hit the primary. Boom, I hit the primary. Hit the secondary. Boom, I hit the secondary. You come down, and you miss the little part that they're taking the picture with. So it's really a shame. All that. So you spend all this money making a huge telescope. These are hundreds of millions of dollars. You bring all this light to focus, and you only take part of it. Why? Mainly because detectors cost a lot of money. So there are some new detector telescope projects where they want to actually use all that light. And once the Large Synoptic Survey Telescope with CCD is about this big, filled up 3.2 gigapixel camera, and probably people would try to do that more in the infrared if you can get the price per pixel.
Okay, I think we'll end there. No more questions. Let's thank Jim again. Thank you.